We're not going to look at the developer so much, but we'll go back to our algorithms. Let me find them first. Oh yeah, so where are we here, right? So I'll close this. So we are, we look at the Bogos sort, and let's see again. So we already talked about this. What's the worst case performance, or well, expected performance involves some factorials, right? So first of all, I'll generate some random numbers. I'll use the list for now, but you know, from 1 to million random numbers, right, up to 6 numbers, right? So random 6 numbers, right? And actually, let me do time it on this, right? Again, so just single time it. It's going to be single running. Yeah, 0 seconds. So very quick. I was got very lucky, right? But it's sorted, right? So now if I do a timing, of course, right, it will be very quick. Why? Because it's already sorted. We already figured this out. Right. But let's go to how many numbers should we sort? 9? Let's do 9. 9 I think we can do. 10 I don't really want to do it today, but I'll do 9, right? So 7, I'll do time it. Yeah, 0 seconds, right. Well, anyways, so 8, still 0 seconds, so 9. Okay, 1 second already. So in 1 second sort 9 numbers, that's already getting kind of bad. So now, like last time I was not lucky, I didn't get 10 sorted. Do you want to risk it?
Yes.
All right, let's do it. Let's do it. Maybe we can do it today. Maybe. Oh, this maybe. Oh, 5 seconds. That's pretty lucky, right? So yeah. So again, now of course I have ruined all these random numbers because they're not random anymore, right? They're all sorted now, right? Because it's in place, right? So again, I'm not going to do it anymore. What I want to show you is now the factorial part, right? So, factorial of 10, so we have 10 ways of picking the first number, 9 ways of picking second number, and so on, right? You guys all know what factorial is, right? Mm-hmm. So that's where the number comes. So it's about on average, about 3.6 million operations, but that's of course just basic iterations of our algorithm, right? On average, right? But that's average. Sometimes you can make it lucky, right? If the day is bad, maybe it takes you 10 million times, right? So, I mean, theoretically, it could take forever, right? Theoretically, if you're really unlucky, right? If you're really lucky, you get to the first try, right? That's the beauty of random algorithms, right? So, again, so here is somebody was mentioning there's a visualization. If you have a link to this, let me know, to this visualization of this. Was it one of the, on a YouTube or anywhere else, right? I'll embed it here. But math factorial 20, hopefully you'll agree, and this is average case, right? Right? So, I don't want to count the zeros, that's pretty big. That's about probably like, what is it, 3 million, billion, trillion, quadrillion, like 2 quintillion or something like that, right? So, not going to happen, not in our lifetime, right? So, yeah. Like I said, you're welcome to leave a computer aside, set a computer aside, maybe you get lucky, right?
But if we run it on the RTU supercomputer.
Yeah, but so that's the whole idea, right? Even, that's the whole thing about complexity analysis is important, right? Even if you have a nice parallel supercomputer, right? You buy the NVIDIA, rack of NVIDIA hardware H100, 800, right? And everything, you run in parallel and everything. It's still not going to matter. You might be able to shave like 1 or 2 zeros, maybe 1 or 2 zeros, maybe 3 zeros, right? Make it 1,000 times faster, 10,000 times faster, maybe 5 zeros. You think, okay, that's great. Then you try to sort 5 numbers, and those zeros are useless basically, right? You already, maybe you gain you can sort a few more numbers. That's why currently in AI research, there's a big discussion on this, right? So we got these big improvements on hardware, right, in the last 5 years or so. We got big improvement in large language models, right? But now the discussion is, maybe we have reached this top, we are throwing this more expensive hardware, right? Companies are spending billions, Meta, Google, Microsoft, everybody's spending billions on NVIDIA hardware, but maybe the improvement is going to be very tiny now, it looks like. Maybe have you reached the peak? right? Or maybe we'll get something really cool, right? We don't know yet, right? We'll wait for ChatGPT 5. We don't know, it's good coming out this fall, hopefully, right? So that's a discussion. There's this discussion like in the back, sort of, maybe nothing good is going to, I mean, maybe that's it, maybe for now. Maybe we need something else now. You know, this is good, LLM is good, maybe we need some other technologies, you know. So maybe to combine them with something else, right? Because we have reached this, you know, this performance. We can make small gains, maybe small gains, right? So we don't know yet. We'll see. But here too, right? So throwing more. So the whole idea of complexity is throwing more hardware, right? If your algorithm is really bad, throwing more hardware is not gonna help you. Okay, right? So that's the key takeaway. I'm gonna delete some. Right. So what I'll do is also I'm gonna delete all the bad code. Yeah. So we get to even if we could have faster hardware, or even if we could somehow parallelize the algorithm. I don't know how can you parallelize Bogos sort. Check, maybe do sorting, some, I don't know, shuffle. Still wildly impractical. Hopefully you all believe me. Now I'll go back. I'll delete all these extra cells. I'll go back and restart this because I need to regenerate because I already ruined them. Okay, now bubble sort. So bubble sort. Where's the bubble sort? You might have. It's pretty famous because it's one of the earliest ones. You might already know. All of you might already know bubble sort, right? You might have encountered it, right? Because it's very simple to learn, right? So bubble sort. So what's the idea of bubble sort? Who remembers?
You bring the biggest number to the top.
Yeah, but basically, you just go past. You do passes. You know, you iterate, and if the bigger one goes, you swap them. You swap the numbers, basically, right? So extremely simple to write, right? As far as programming goes, right? This is usually the first one. Usually people don't teach bubble sort, right? Usually bubble sort, we start with bubble sort, right? So it's simple to write, right? And it's the good news is it's going to be faster than bubble sort, right? So that's the good news. To me,
Sometimes.
Sometimes. Maybe if you are really good with random numbers, maybe you are very lucky with bubble sort, right? So that's the thing with bubble sort as well. So exchange. You can see a visualization here, right? You start here. So one of the properties is that by bubbling, right? What is guaranteed? Yeah, you see here, yeah. So if you're doing this kind of bubbling, no matter where you start, at the end, this is one pass, right? So it's 1, 2, 3, you know, one loop, right? At the end of this one loop, the last number will be in place, right? It's guaranteed. This will be the largest number, right? Think about it, right? You have in your list or your array, you have a largest number somewhere, right? When you're doing bubbling, inevitably, it's going to bubble up to the top, right? To the last place, right? It's bubbled there. Right? And of course, you can see now, hopefully you can see this if you keep bubbling, but the second run, right? The second will be bubbling up here, right? Second to the last, right? Because the biggest is already here, the second biggest also will bubble up, right? And so on and so on. So hopefully you can see this value. Hopefully by now you already trust me enough, right? That it's all going to be sorted eventually, right? You do enough bubbles, right? These exchanges, right? And it will be sorted. But the only question, of course, is how long does it take, right? What's the complexity of this, right? Well, again, already here the cheat sheet is called n squared, right? So why? Let's think about this why.
Because you need the double for loop nested.
Yeah, it's basically double nested loop. It's loop within a loop, basically, right? So you have to do this n times. You have n runs n times, right? So this whole thing happens n times. There's 9 items, so you have 9 times 9. Actually, it's a little bit less than n squared, but in complexity analysis, if it's like n squared minus n, for example, right? So one of the things is that, like, you have maybe, when somebody writes on square, right? It's actually, right? So you say on square minus n, right? As far as complexity, this n doesn't matter, right? This doesn't matter. Even if it's like n squared minus 1000, right? 2000, right? Only the highest, right? Highest term matters. This matters, right? Again, because it's not a precise, not like algebra. It's basically a tool for estimating how good or how bad the algorithm is for large numbers. Because if you think about it, right? This term, this n, right? This algorithm is going to be slower than something like n, right? Eventually, right? You think, okay? Maybe for small algorithms, very quickly, this small n is not going to matter. This square is going to matter, right? In a couple of lectures, we'll talk about how to estimate, how to calculate this complexity. Right now, if we see loop within loop, so loop, loop, and loop, right? Nested loop, right? Nested, right? So, okay, so bubble sort, it works. It's easy to write. You should probably not use it if you can, right? It's the most inefficient as far as of algorithms which actually people use them sometimes, right? In fact, there's funny some OS somewhere use bubble sort somewhere like some. So there is something useful about bubble sort, which makes it maybe slightly better than some other algorithms sometimes. Notice here bubble sort, right? The best case scenario, in fact here I'll make this bigger, right? So this omega, right? People will usually talk about O, but actually we have three letters. We have omega, theta, which is actually usually what we think about. Theta is average, usually the lower bound, right? The best case scenario is omega, right? I'm very informal, talking this informally right now. Definitions comes later, as we get intuition. So omega, best case scenario, bubble sort, ON. What does it mean? This means you do a one run, you check if it's sorted, and we are done, right? If somebody give you a sorted list, already bubble sort is not going to do any extra work. So that's good, right? Of course, the thing is on average and worst case. So in a way it's good. If you are not lucky, somebody gives you a completely scrambled list, bubble sort will do n squared. On average also, the bad news is this part here, right? This is the really bad news. Because especially because we can avoid. We'll see there much better algorithms. Okay, so implementation. I won't spend too much time on it. Also, since I want to keep the original, right? I'm going to add a copy here, right? This is actually keep in place. Keep in mind, copy costs time and memory, right? So not always optimal, right? Right. So I'm going to copy because I want to keep the original, right? And then I say, okay, well, exchange. So this is the outside loop, right? So we have exchange count, right? While it's over 0, I wonder why do I need this 0? Oh yeah, because I need star. Yeah, so this is a little hacky here because I set it to 1 and then I start 0. Idea being we need to do one run, right? We need to do one run, and then if we have no exchanges, this means if you don't have any swaps, what does it mean?
It's sorted.
Yeah, it's sorted, so we can quit, right? So outer loop quits when this inner loop runs once, right? So ON, that's where ON comes in. Best case scenario, omega n, right? And if I said that the debug is just a flag for printing out numbers, so let's see how it works. So I have my list. Oh, this is big. I can sort this one. It's too big. I need something shorter, right? Let's see. This was not the. Hold it. I need. Here. There you go. Now I'll check. Yeah. Is this sorted? Not quite, right? So, remember I told you, we should be getting, this should be going to the end here on 66 as we saw previously, right? will go second, third, and so on. Let's take a look. Still the same place, right? So first is sorted. Remember, this took how many runs? This whole result of this is after inner loop is finished, right? So ON. So this is ON, right? N run, N, right? So hopefully by now we have 8 runs. So 9 times 8 again. So technically it comes out, if you calculate the loops, it's n squared minus n, right? But this n is not important in this case. It's not important. Okay. So you trust me on this right now? Yeah. Okay. Okay. Let's do one more bubble, right? So 0 seconds. So we'll do some timing. Time it. It is 170 milliseconds. So for 1,000 items, it's less than a second. It's 1,000 items. We know at least not factorial, but that's not so good, right? So if I do bubble sort for 10,000, so how much do you think? What do you think it will be? How long will it take? Roughly. Any ideas? If this takes 170 milliseconds.
10,000
Not 10,000 is more, but how many times more? You have 10 more time. So this is 1,000 and this is 10,000, right? Yeah, exactly. So hard time. So I would say 15, 17 seconds, roughly, right? Last time it was, well, actually interrupted last time, right? But I think this will be about, I would say, I'm going to risk it, but because I can keep talking while this runs. I'll run it, right? I'm saying about 20 seconds, so this means it will take about 2 minutes. Why 2 minutes? Because it does 7 runs, right? You can't avoid this, so 7 runs, 1 loop each, so it'll be about a minute and a half while it does it, right? And I can talk about this meanwhile, right? So again, so just imagine, so 10,000. So the story goes, why quadratic is considered, this is considered most dangerous complexity, because you can miss it. You have 100 items, it works. 1,000 items, 170 milliseconds, right? But you have 10,000 items, and suddenly it gets slow, right? And this was the case with the game GTA, I think 5 online, I think, right? A couple of years ago, actually there was a loading screen which kept getting longer and longer and longer. You might have read the story, right? And what happened is there was hidden quadratic complexity. So people, they tested the game studio, Rockstar Games tested it. Some poor guy who was tasked with doing this, he tested this with 1,000 items, and it worked, right? He didn't notice. But people are getting more items, meaning the inventories grew, right? And with 10,000 items, this quadratic complexity led to 10-minute loading screen, or basically, right? So really, evil. This n square is kind of evil because you can miss it basically, right? You don't do enough testing, and if you basically think, okay, sometimes it's hidden, right? Sometimes a loop, right? You think, oh, this is just one loop. But maybe you do something in a loop which is also a loop, right? And if it's hidden, that's what's the case with GTA. This actually is a Latvian blog, but it's not a Latvian. I don't think it's a Latvian guy who found this, right? But it is published in a Latvian blog. And Rockstar said, okay, yeah, this is a nice fix. We'll fix it, right? Because yeah. So I was doing it. I can find it. Rockstar GTA Online JSON quadratic. Yeah, this guy here. But this guy here, Neil LV, that was said 3 years ago, right? This is the link, right? GT Online, right? So 6 minutes, right? Is load. That used to be the case, right? Where did this happen, right? So he was doing some testing, right? Of course, profile again. So I really admire this, right? Yeah. Yeah, so basically it was in string, the hidden was in the C language call to string length, basically, right? So this is kind of seems like really hidden, meaning testing the length of the string, basically, right? Meaning to find the length of the string using C language, right, you have to actually count how many characters, right? So that's where it is basically hidden, like it looked like a loop, but it's inside string because you expect the length of the string would be a fixed type, O1, but it wasn't in this case, it's ON, right? And if you fix this right, you use different data structure, right, then you'll be fine, right, yeah. Right, scan, right, this is a way of parsing JSON, basically, right? Yeah, so pretty cool stuff. Yeah.
How does he get access to the source code?
He didn't. He actually he used debugger. You see, I said the assembler. This assembler, right? Well, notice also. I like how he wrote. I borrowed my friend's completely legitimate copy of industry standard disassembler. Obviously, he used the pirated version, obviously, right? So friends, right? Yeah, it's very expensive. These assemblers, right, are expensive. But basically, he looked at the assembly code, so he doesn't see the original code, right? So he can see. Yeah. 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 So basically, he had to also break. There was also the code, of course. Obviously, most modern games and most things, applications have extra step where the code is, obfuscated, right? Meaning messed up on purpose, so this assembler can't do everything. It's not easy to see what's happening, right? For various reasons, so you don't have an easy time breaking copy protection, right? Not that it has ever stopped anybody, right? Well, but yeah. So yeah, this is really cool, actually. Like I said, and yes. Somebody asked me, was I someone of the students asked me, was I the one who did it? No, I didn't do it. No, but it's cool.
But hypothetically, we can take any program run
Yeah.
this assembler.
Yeah, and you're using your friend's completely legitimate copy, right, of industry standard disassembler. Yeah, you can check this. Yeah, you can see.
And then we can compile the assembler code.
Yeah, you can go back, right? But of course, but the thing is, of course, that's why obfuscation works to some extent in pretty much most language. Right? You lose the variable names, things like that, right?
Yeah.
You don't have all the things which make life easy and enjoyable, right? You can see what the code is doing, but if it's a large program, right, you need some experience to get to the right area, right? You sort of do. You need to use binary search to find exactly where things happen, right? You need some ways to find it, because I mean, just imagine if you had to go all these these are low-level instructions, and move things around, right?
Have you ever used it?
Yes, I've used it, yes, but not for not for GTA, right? Yeah, it's fun. Yeah, and of course, this whole industry, white hat, gray hat, black hat, but white hat, of course, is good, right? There's also job opportunities here, right? So, good stuff. So now we go back to our basic sorting algorithm. So, remember, quadratic bad. So let's look at another sorting algorithm. Yes, bubble sort. Let's look at selection sort. All right. So what's the idea of this? Idea is to do these passes. It's kind of similar to idea is a little bit similar to bubble sort because also pretty famous algorithm. Also similarly, I'll skip ahead. Is it good? No, it's not good. It's almost as bad as bubble sort as far as complexity goes. This algorithm. Idea is we go through our array and we sort of keep in mind we don't swap the values. We just keep in mind, we keep which one is current largest, and the current largest you put it at the end, right? Select, put it in the end. So it performs very similarly as bubble sort, right? The progress at the first run, again, n times. We have to do it n times, right? Except the only thing what we do gain is it's in practice it's faster. Because you don't do so many swaps, basically, right? You just keep the current maximum. In memory, right, you don't need to do this swapping. Because swapping, actually, memory is a relatively expensive operation, right? So, if you don't need to swap, you avoid it. But it's just the same bad n squared for complexity, right? So, I can show you ON, right? Selection sort, right? So we find the max, current max, the index, and we go through, so outer loop, inner loop, right? In fact, there is even one worse problem with selection sort. I want to touch on this, right? Selection sort, notice what's the problem. That's why This is generally not a good algorithm at all. Look at this here, right? So you do this no matter what. Even if somebody gives you a sorted list, you'll still look for the largest, right? There's no provision for stopping, right? So you do this no matter what. So this is like almost, in some ways, worse than bubble sort, because in real life, it's very rare you get completely random numbers, right? Usually your data has some sort of order, right? Maybe it's partially sorted, right? So in some ways, you want an algorithm which has some provision for stopping early, right? Maybe you can utilize, so the best sorting algorithms utilize this, right? Because if you care about real-time performance, right? If you get data which is almost sorted, you want the algorithm to use that to your advantage. So selection sort is just a really dumb algorithm in a way. It looks for the maximum, then for the next maximum, and so on and so on and so on, right? It works, you can see, I think we can all see how it works, right? But not a good algorithm. But it can lead, and you might say, okay, why even look at it? You'll see this in the next lecture, that it can lead to a better algorithm, right? Because just imagine, for selection sort, right? We have task, get maximum of things, not counting the thing we already have the max, right? So here we need to look maximum over all, right? Then we need to look maximum here, right? Which is 66, right? Basically, yeah. Yeah. So this is after the first run. We need to find the maximum from here, right? Which is 66, right? We need to find maximum from here, which is 34. Didn't have to do anything, right? It's almost sorted. But if you don't, the selection sort doesn't care about this. But the thing is, if you think about it, which might seem a little bit maybe fantastic, what if there's a way of picking the maximum quicker, right, than linear? Can we do it? Well, it turns out we can, right? That's next lecture we don't talk about, but it's if we could somehow pick up the maximum value quicker, right, by doing specific data structure, then we could beat this time. If we could make a good algorithm of this, we could make something called heap sort out of the selection sort. So that's a cool thing. So selection sort is by itself bad, but it can be served by modifying. And that's a lesson for you guys. You can see a bad algorithm, maybe you can make it better, right? Maybe you can use some parts of this existing bad algorithm to see if maybe there's some place we can optimize. It turns out we can, right? So selection sort is not so great. But also next one is insertion sort. And I know when you're starting to learn insertion selection, for me I was always messing them up. Which one is insertion, which is selection? So insertion is the card, the way we would sort playing cards, right? You have a bunch of cards, right? And then you say, okay, you take one card, right? It's sorted, right, by itself. But then you take second card from your unsorted part, right? And okay, my one card is sorted. Is it my second card stronger or weaker? Okay, I'll put it weaker. I'll put it here. So you start sorting. You build up the sorted part, right? Sort of from the front, basically, right? The difference is that 54, right, is not necessarily the smallest, right, or biggest. That's in this case smallest. We say 54, beginning, it's sorted, right? First one item sorted. Two items, we take 26, we see, okay, where do we put it? Insertion, right? You take 93, where does it go? Here, right? Where does 17 go? In the beginning, right? 77, inserted. So this is always, we build up, this says guaranteed sorted, sorted, right? So, we insert, meaning the idea is this, look at this, we are not going to the end, right? Here, in this part here, I'm not going to the end. I don't even know anything about the end of this, right? In this step. So this looks almost more efficient, right? Well, the bad news is this is still n squared, right? But on average, it has better performance. In fact, even though you say, okay, I just told you n squared is bad, insertion sort is often used for sorting smaller items, like up to 50, right? It's used as basis for more complex sorts as a sort of first step, because it has a good property. First of all, if it's almost sorted, right, you can sort of like, it will do like the bare minimum needed, basically, right? So it works very well for almost sorted data. If you check here, insert and sort, right, ON. But unlike bubble sort, right, this actually often, this ON is actually, even for slightly sorted data, it will still perform well, right? So if you have completely random data, you don't really want to use insert and sort. If you have a lot of data, you don't want to use insert and sort. But if you have small amount of data, maybe up to 50, maybe insertion sort actually might be decent enough. If you know, you're not going to need more items, right? So, only thing, it's a little bit more hard, maybe tiny bit hard to write from scratch, right? So, insert and sort, but not too bad. Again, outer loop, inner loop, right? So, outer loop, we start in the beginning, right? First item, right? That's our setup, right? The first item, we know, of course, right, is sorted, right? And we check. Next item, right, we swap, basically, right? So, on average, right, if you do the tests, you will see that it is actually slightly faster, right? Again, you can see here, look at how it works. In this case, of course, we did up to here, right? We don't really see the sorted list, right? But here, we see it here already, right? So, up to here, it's sorted here, right, here, no, up to here, right? So this is sorted, right? And again, we don't look at these here down, right? In these runs, we only doing this here, right? So we're inserting, right? So I take 66 and say, okay, where do I put it? Do I have to put here? No, here, here, here. Of course, you can see that it kind of we shift this linear complexity, this quadratic complexity to the end. So here, this is where the most work has to be done, right? Because I have to go through this 200 last step, right? I have to put, where do I put this 221, right? Well, at the end, right? And then I'm finished, of course, here, right? So, time it, right? Again, can I do 10,000? Actually, by the way, I didn't check how much was the selection sort. Oh, selection sort was 2 seconds. Did we actually do the bubble sort? That's 100,000, no. Where's my 10,000? Yeah, 20 seconds. 20 seconds. So roughly, right? Yeah. There's slightly more overhead, right? But yeah. So about 10 to 100 times slower. So insertion sort. Do we want to do 10,000? So 1,000. Should be. Yeah, it's about half time. It's about half times. 2 times faster than bubble sort, right? So again, constant factor, that the same complexity, right? But still, I mean, if you are called at gunpoint, choose insertion sort, right? Instead of bubble sort, right? You have choice. 2 bad choices, right? Still have choice, right? So yeah, I'm not don't have much time to run the insertion sort. You can do it at home. I want to get to at least one more good. I want to get to one good sort at least before the end, right? Yeah, so merge sort is done by John von Neumann. I might have mentioned him before. Did I mention him, right?
Yes.
Yeah, the polymath, right? The guy who knew everything. One of the last guys who knew everything about math, basically, right? He's also called one of the Martians. There's a bunch of Hungarian guys who came to, lots of scientists from one high school, actually, right? Like in Budapest, right? In the early 20th century. There's a bunch of Nobel Prize, bunch of everything. It's like, how did that happen? The explanation is they're all Martians, basically, right? So, but yeah, he was the most famous one, right? His teachers are scared of him. So, and his neighbors too, right? He liked to play German marching band at night or something, right? And so, wild guy. But yeah, anyways, he just happened. Of course, he invented his von Neumann architecture, and he also invented the merge sort, one of the first good algorithms. Right, he didn't do bad things. Well, he did some bad things, but of course, as algorithms goes, right, he wanted to nuke, right? He wanted to nuke. If he advocated for nuking the Soviet Union before the Soviet Union got the bomb. So, right, so we're kind of lucky he didn't get his way, right? So, yeah. So, but let's go back to his good deeds. His game theory, he said, okay. Right, we should, we have the advantage, right? We should win right now. We have a chance to win, right? So, yeah, he was not really thinking things. on some other level, basically. But yeah, so merge sort. What's the idea? Again, going back to insertion sort. One item is sorted. You have one item, it's sorted. You have no items, also sorted, right? So with that, those two sort of base cases, right? We can build on this. So idea of merger is really kind of cool. So basically, you divide everything within one unit, or possibly nothing, but basically one unit, one item, and you know it's sorted, right? This is sorted, 54 is sorted, 26 is sorted, 93 is sorted. All these are sorted, right? And it seems like a really weird idea, but notice this. So this part here, this division is what complexity? How much time does it take? Long, yeah, you see this because yeah, you divide in half, then you have these operations. The turns out this is log n, right? So your outer loop is only log n. So that's the trick, right? Well, okay, but how do you go back, right? then that's where the merge come in. Merge part comes in. So this is merge. So basically, 54, 26. It turns out it's linear complexity to merge linear lists, right? So we have to do this. So on to divide, and so on all log n times, right? We have to do this part here, right? So 1, 2, 3, 4, 5 times, right? So you had like, let's say you have, 30, how many items? You have 10 items, yeah. So a little bit over log 2, right? Doesn't matter. And linear. So it turns out there's linear complexity for merging. So 54, 26, easy, right? 2 items easy to merge, right? So how about 4? We have these 2 items, right? So what's the algorithm? So that here's a slightly tricky part about merge sort. How do you merge these 2 in linear time?
You check
Yeah.
the first element. And
Yes, you keep going. Yes. So you check which one is smallest. At that moment, you know, okay, either this one is going to be smallest or this one is going to be smallest. We keep the sort of like pointers, basically, right? We keep reference to the current lowest, right, where we are in both lists. So what happens if you go through one of the lists, one of these arrays is over? What do? Then you know the rest is going to be from the second. You take everything from the second. So this merging is linear, right? And that's how we keep merging, right? Of course, practical implementation, it's a little bit tricky if you don't have good powers of 2. Like in this case, you have 1, 2, 3, 4. You don't have 8. You have 9 items. You see, there's a little bit. It's not always same size. That's when you're programming. You can make some tiny one-off errors somehow, right? But otherwise, as far as the algorithm goes, right, it's pretty easy to see how it works. Okay, so n log n. So merge sort is really good. You can still use it, right? Now, if you check here, right, only one downside is this part here. It's also kind of like selection, so it doesn't care if it's sorted or not. It does this splitting and it does this merging. So it runs same no matter what happens, whether you have almost sorted items or just completely random or completely sorted or reversed items, right? So that's the downside. It's on average, it's still you can't, you have a million items to sort. Merge sort will be good. It turns out actually merge sort is used often as a basis for sorting more items. Team sort, right? Who invented team sort? Tim, of course. Who else, right? Yes, Tim Peters, one of the Python guys, actually. There's big drama right now about him actually being thrown off of Python team. But 20 years ago, he wrote TimSort, which is used by many others. Android uses now TimSort. Some other place use TimSort. But it's really simple, actually. Well, not simple, but it's a insertion sort for small items and merge sort for more items, basically, right? So, turns out, in practice, it works faster. If you have almost sorted items, it will pick up on this, right? And then it will use this ability of merge sort for more items for sorting these larger, lists, arrays, and so on and so on. Okay, so this is the first of the good sorts. We won't have. I know we didn't get to the quick sort. We'll look at it next on Thursday, right? So this is the first of the good sorts. And again, all the good these are general sorts. meaning they work for any type of items, not numbers. It could be not only numbers. Could be anything you can compare. It could be strings. Could be buckets of apples. I don't know, whatever, right? So anything. All right. So general. So we'll have to see. Can we do actually even better? That's a question for next lecture. Can we do better? We'll look at some better algorithms as well. Oh, some equally good algorithms such as quicksort, and also we'll look at beating this. Can we beat n log n? What sacrifice do we have to make to beat n log n? Right? N log n is the general best case or the general sorting. There might be exceptions. Okay, so you can do the quiz. Hopefully, right? Do you have access to the quiz? Yeah. Okay. Good. All right. That's it. So I'll see you guys in about half an hour. Right? I'll go around for the charger.
Exactly.